this video we will see some definitions which are used in the chapter of slope and deflection. Now, in some of the definitions, the first definition is deflection. And to explain that, for here I will draw the diagram. I am considering a beam which is simply supported at A and B respectively. Now, suppose there is a load acting at the center of this beam. Now, under the action of this load, the beam is going to get, we can say that the shape is going to change because of the action of load, and I am considering the beam as elastic. So when the load is acting, the beam will deflect in this manner, and when the load is removed, the beam will come back to its original position, which is indicated here. So here the first definition is deflection. I'll say that it is the vertical distance, of the beam measured before and after loading. So here I have written the definition of deflection, that it is the vertical distance of the beam measured before and after loading. That is, before loading the distance is here, and after loading it will reach at this location. So this distance is called as deflection, and it is denoted by Y. In this chapter we are going to denote the deflection by Y. So I can say that the deflection here is Y. Next, deflection at the supports is always 0. At A and B the deflection would be 0. So Y is equal to 0, Y is equal to 0 at A and B respectively. Next, after the deflection definition, the next definition is of slope. Now, slope is the angle turned by the beam. This is theta. So here I'll say that slope, it is the angle in radians measured between the tangent. Here we have the tangent. So the angle measured in radians between the tangent to the elastic curve, and the original axis of the beam. So here, as I can see, that when the beam is bending under the action of load, this curvature of the beam is called as elastic curve, and tangent drawn to the elastic curve, if we take the angle of this tangent with respect to the original axis of the beam, that is called as the slope. And here I can say that slope is denoted by angle theta, or it is simply written as dy by dx. Next, its unit is radian. Now after reaching here, next let us see the boundary conditions. The next case is considering the boundary conditions for simply supported beam and for cantilever beam. Now for a simply supported beam supported at A and B, and suppose the load is acting at the center. Now under the action of this load, the beam is having a length of capital L. When the load is acting, the beam is going to deflect, and here I can say that the deflection at A and B is 0 because it is simply supported. So at A and B, deflection is 0. That is, here I have written the boundary condition for deflection. Next, if I consider the center of this beam, here deflection is maximum. I'll say this is point C. So at C, deflection is maximum, as we can see here. And here when I am getting the deflection maximum, if I draw the tangent, the slope is 0. So at C, slope is 0. Then slope will be maximum at B and at A, theta value. So at A and B, slope is maximum. So here I have written the boundary conditions for a simply supported beam. Next, for a cantilever beam, if the load is acting at the free end, here we have point A, this is point B. Considering the length of the beam as capital L, now under the action of this load, the beam will start to bend ahead of point A, that is, it will start bending from here. And now I can say that first at A, deflection is 0 here, and I can say that also at A, even slope is 0. Slope is also 0. Then at B, here I am getting the deflection as maximum at the free end. For a cantilever beam, the deflection is maximum. So at B, the deflection is max, and at B, the slope is also maximum, because if I draw a tangent here to the elastic curve, that will give me the maximum angle. So at B, the slope is also maximum. So here in this video, we have seen the various definitions for slope and deflection.